Welcome to lecture number 37. Today we are going to start one of our last discussion, right, which is single molecular fluorescence. Now, first question which will come automatically, that why we should bother about this single molecule, right. Till now what we are doing is the fluorescence response of a molecule when it is present in solution, but the concentration is in the order of, typically is in the order of micromolar. So, we are going to have at least 6 into 10 to the power 17 molecules, right, in a liter, right, if it is 1 micromolar. So, that means we are getting a collective response from all the fluorophores present in the solution. Now, in some case, right, this kind of collective response of the molecule present in the solution, right, which is known as ensemble average fluorescence property of the molecule, may be different from the single molecular response of these molecules present in the solution. It will be clear. Let me take one example. For example, you have such a molecule with you. It is made of some DNA base pair, where these base pairs are pairing. These are typically called the molecular beacon. So, here you have a fluorophore and here you have a quencher, right. So, this one is your fluorophore. Let us say it is showing you green color emission. Now, once this quencher is present nearby, then this quencher can quench the fluorescence of this guy, right, and the fluorescence intensity is very low. Let me consider that this is one of the structure of this molecular beacon present in the solution. The other structure of this molecular beacon which is present in the solution could be in the open form. So, this is my closed form and the other one is my open form. So, here is your fluorophore and here is your quencher. Now, as the quencher molecule is far apart from this fluorophore, obviously the fluorescence intensity in this case will be much more compared to the other case, compared to the closed form, right. So, this is your fluorophore and this is your quencher over here, and this is your fluorophore. And this I refer to as the open form. Consider that I know the emission spectra of this closed form and this open form. Understandably, the fluorescence intensity of this closed form will be much smaller and the fluorescence intensity of this open form is much stronger, right. So, if I now draw the fluorescence intensity of this closed form and open form, what you are going to see is, let us say this is the fluorescence spectrum of the closed form, lambda emission versus intensity, this is the closed, and let us say this is the fluorescence intensity of the open form. Now, consider you have taken this molecule in a different solvent and what you are getting experimentally is something like this. Now, my question is, this is your measurement. So, my question is, what is your conclusion? Number 1, you can conclude it like this way, that 50% of these particular molecule is present in the closed form and 50% of this molecule is present in the open form, and as a result 50% will show the low intensity, 50% will show the high intensity, and altogether it is showing the moderately intense fluorescence. So, the option 1 is your 50% closed and 50% open. But there could be another situation, because you are doing this experiment in a different solvent, right. So, in that particular solvent it is also possible that all of them are having a particular form which is neither open form nor the closed form, it is intermediate. So, that the quenching is right, the quenching of the fluorescence by this quencher is not that much permissible, and you are getting a moderately intense fluorescence intensity. For example, what I want to say is that let us say this is the situation, right, another type of form. So, I will name it as partially open form, it is not fully open, partially open form. So, in this case what you will going to get is moderate intense fluorescence, right, because the quencher is not very far, not very close, here is very close, here is far, but here is not very far or very close, right. So, probably this fluorescence intensity will going to give you this moderately intense fluorescence intensity. So, the second option could be that all these molecules under investigation, right, you have certain concentration, but all of them are present in a partially open form, right. So, all of them are present in a partially open form. Now, if I ask you which one is correct of this one, A1 or 2, which one is correct? If you are just simply doing the ensemble average fluorescence spectroscopy with this fluorescence spectroscopy, it is impossible for you to tell which one is the correct explanation, correct. You may say that okay, let me measure the anisotropy. Even you measure the anisotropy, as you know, in this case as it is in the compact structure for the closed form, then the steady state anisotropy will be smaller, and in this open form the steady state anisotropy will be larger. But as a mixture, because in anisotropy we are looking all the molecules together, right. So, we cannot distinguish whether it is partially open or fully open, it is a mixture of fully open and fully closed, or it is just all of them are partially open. So, we cannot do. The only solution is that we have to look this molecule individually. Suppose you are doing this experiment individually, how I will come later, but consider that you have the technique so that you can measure the fluorescence intensity of such molecule one by one. Right. Now, you are measuring for the molecule number 1, right. Next you are measuring for molecule number 2, next you are measuring for molecule number 3, and so on and so on and so on, right. In that case, what you will going to see? You will going to see two different, depending on the two different case, right. If it is the case number 1, right, then the fluorescence intensity versus the number of molecule. So, here is intensity, here the which molecule you are measuring. So, number. So, you are measuring the molecule now, number 1 molecule, then second molecule, then third molecule, then fourth molecule, and fifth, so on and so forth, right. So, number of molecule, or I can change this number of molecule to something else. Let us say you are measuring from this is your sample cell, right, and you are measuring from here, and you let the molecule to come one by one here and let it go out of this. So, molecule is coming, once it is entering in this region, you can see fluorescence because you are measuring from here, and when the molecule will leave from here, you will not be able to see the fluorescence. So, say number 1 molecule is coming, entering, and it is going to give you the fluorescence, and when it will leave, you will not going to see any fluorescence. Then probably the second one will come, you will enter here, and then you will see the fluorescence, and when it will leave from here, then you will not going to see any fluorescence. So, this number of molecule I can, for such kind of arrangement, I can replace with the time, right. So, for the continuous monitoring process. So, here I can also refer this as a time, right, for a specific observation volume. In this case, what we are going to see, if it is the case 1, right, you will see the fluorescence intensity probably is 0, because none of the molecules were present inside this observation volume. Then fluorescence intensity will increase, right, and then fluorescence intensity again decrease. Then again probably another molecule will enter, fluorescence intensity increase. But when the third one will enter, right, when the third one will enter, it probably the fluorescence intensity is less, right, because it is now the closed form which is entering. So, I should redraw it properly. So, the first one is entering, fluorescence intensity is high, then when it will leave, fluorescence intensity will be less. When second one is entering, let us say it is also the open form, sorry, it is also the open form, yes, then fluorescence intensity is very high, and when it will leave, fluorescence intensity is less. When the third one will enter, right, then fluorescence intensity is too low because it is in the closed form. The fourth one is like this, fifth one is like this, sixth one probably like this, and so on. So, you will get such kind of fluorescence intensity versus time plot for this observation volume. So, this is for the case 1. However, in case 2, what you are going to see is whenever the molecule will enter this observation volume, the fluorescence intensity which we will get from this observation volume will be fixed, right. It will not going to depend molecule to molecule which molecule is entering, because all of them are partially open, right. It is not like that, some are fully open and some are fully closed. So, in this case what will it is not necessarily that at the same time we are going to see the fluorescence burst coming out of the observation volume, it is not necessary, right. So, but whenever you will going to see, it will be of moderate intensity like this, whenever it will come, clear, like this. So, you see the basic difference. So, from your experiment, if you look at that how this fluorescence fluctuation is happening, you will be able to tell clearly that okay, what my proposition is number 1 is 50% closed or 50% open is correct, or whether my proposition that all of them are present in a partially open form is correct. So, for that what I need to see? I need to see the fluorescence characteristic of a single molecule of this particular biomolecule, right. Moreover, let us say I can also say that somehow I came to know that this is present in the partially open form, Now, I can think of that this is the structure of the partially open form, and this structure remain fixed, right, throughout the time, right. What I mean is that there is no fluctuation in the structure, but recent studies like this can be represented as a protein, right. Recent studies are suggesting that the protein structure which we used to see in the textbooks, right, the PDB structure, the crystallographic structure of the protein, they are not rigid, right, in solution. In solution, they undergo a slow breathing type of motion, the time scale is very slow, is in the order of few microsecond to tens or 20s of microsecond, right. But they are undergoing a slow breathing motion, right, and those breathing motions can be captured by using such kind of single molecular technique. What I want to say is that the conformational fluctuation dynamics, right, may also change the fluorescence property of such kind of molecule, right. For example, if because of this conformational fluctuation, this quencher will come little close or far from this original position. When this quencher will come at this position, quenching will be more. When this one will go here, then quenching will be less. That means there will be some fluorescence intensity fluctuation, right, within this molecule. There is not much change in the structure, right. Both are partially open form, but there is small change in the structure, right, within this partially open form. It is not that it is converting between the closed form and open form, not that big fluctuation, right, small fluctuation, but that small fluctuation is good enough to change the fluorescence characteristics of this molecule, right. So, such kind of slow conformational fluctuation dynamics can also be observed, and in such case, if you now do such kind of plot, what you will going to see? You will going to see such kind of diagram. In all the cases, it is similar intensity, but within this similar intensity, there is some sort of fluctuation. There is some sort of fluctuation. Sometimes it is high, sometimes it is low, right? Sometimes like this. So, that can be used further to calculate the conformational fluctuation dynamics. Okay, so just for your reference, I will write here this conformational fluctuation dynamics. Okay, I have to make it more clear to you, I have this PPT slide for you. Here you see, let us say this is my protein molecule, right, and this protein molecule, the fluorophore is present in this location and the quencher is present at this location. So, when they are far apart, I can see a strong fluorescence, strong pink fluorescence, right, just I have described like that. And when they are close by, so in this case you see they are close by, that is what I have made this cartoon. So, when they are close by, the fluorescence intensity is less, right. So, in this case, in the solution probably such molecule exists, such molecule also exists, such a molecule also exists, such a molecule exists, and many such kind of molecules will exist together, right. When one molecule is unfolding, when one molecule is going from the closed to open and many other form in between, right, closed one and this open one, but many other form between, that is my conformational fluctuation. Like molecules are doing like this way, right. In case all the molecules are opening and closing simultaneously in a coherent fashion, that means one molecule, when this molecule is doing like this molecule is also doing like this, then when this molecule is like this molecule simultaneously like this, right. So, in that case, in the coherent fashion, if everything is going to do like this, then ensemble average picture is good enough to see the fluorescence fluctuation of this molecule, because all the molecules are changing its conformation, right, simultaneously, right, in a coherent fashion, right. But so then I will see that fluorescence intensity will increase, then fluorescence intensity will decrease, increase, decrease, and so on and so forth. But if it is not, here in this particular scenario, as I am showing here, at a particular instance they say this is a particular instance in time. This molecule, here see, look here, this molecule is showing strong fluorescence, this is weak fluorescence, this is strong, this is very strong, this is weak, like here are different. So, still as I can see by my eye in this particular PPT slide that okay, this is strong, so this must be open, this is strong, this must be open, this is closed, so this is weak, so this must be closed, and so on and so forth. But it is possible for me because I have only 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 20, only 22 such molecules are there. Consider you have Avogadro number, let us say micromolar, so 10 to the power 17 molecules per liter, right. So, in such case, let us see this animation. So, you have several such kind of molecules, right. So, it is a huge number, 10 to the power 17 molecules are present in the solution. So, in this case, what you will going to see from far apart, I cannot distinguish this different color of different biomolecules present in my sample. That means, the information of intensity fluctuation is now lost, right, I cannot see. So, for me that all these color are equal, right, from here to here it looks like a single color, right, I cannot distinguish this. So, in this case what is the solution? My solution is that I cannot see these molecules in an ensemble average picture, right, not together. If I am going to see all these biomolecules together, then I will lose such kind of important information, that is the fluctuation of the fluorescence intensity, right, with time. What I have to do? I have to see such kind of biomolecule individually. I have to see these biomolecules, and that is my goal. How to achieve? That is what we are going to discuss here. Okay, so my aim is that these see individual biomolecules, right, as I have shown here. So, we need to investigate a single protein in biomolecule with time resolution of the conformational fluctuation, right. If I am going to see only this one, then I will be able to tell that with time how these biomolecules actually fluctuating. If it is fluctuating, that means its fluorescence intensity must fluctuate, because I have a fluorophore over here and I have a coenzyme present over here. So, if it fluctuates, its fluorescence intensity must fluctuate. So, if I just sitting over on this particular biomolecule and see how the fluorescence intensity is changing with time, then I should be able to comment on the conformational fluctuation dynamics of this biomolecule. So, for to show this, I have this animation with me. As you can see here, that when this is in the closed form, fluorescence intensity is less, when it is in the open form, fluorescence intensity is more. You can see this as you are seeing only one molecule. As I showed earlier, for several molecules such kind of fluctuation information is lost, right, because many molecules are present, and because this is non-coherent in nature, right. So, I showed you the importance of this fluorescence, single molecule fluorescence. The first one is that you will be able to say that what kind of structure it is, and the second one you can also able to determine that with time, right, how the structure is changing. Next, I would like to show you another advantage of the single molecule spectroscopy by showing this type of reaction. So, here let me have a reaction, a substrate labeled with fluorophore. So, F is my fluorophore and it is getting bonded with this enzyme to form some enzyme substrate complex, which is denoted like this EQ, and ultimately this is going to give you the product ASF and this enzyme back, right. So, if you want to study the kinetics of this reaction, what you should do? You should I am talking about our normal fluorimetric assay of this enzymatic reaction. So, in that case what you should do, you should take your SF or EQ in the cuvette, right. Let me take EQ in the cuvette, and then if you add this SF initially, right, if you follow with as a function of time the fluorescence intensity, initially the fluorescence intensity must be 0, right. Let me change the color. Initially the fluorescence intensity must be 0 because EQ, right, does not contain any fluorophore. So, fluorescence intensity should be 0 over here. Once you add this SF in the mixture, right, then the EQ will react with SF to form this free fluorophore, right. So, with time the fluorescence intensity of this will increase, and when the reaction will complete, all the SF will be converted to S plus F, and then fluorescence intensity will be maxima. So, from here you will be able to say what is the rate constant of this reaction, and you can now change the effect temperature, you can change the environment and see how the enzymatic reaction is actually depending on those cases. But now consider that when you are mixing SF with EQ, obviously you need some time, right, you need some time. So, whether you will be able to monitor this enzymatic reaction, right, that will be guided by the date time of mixing, right. This is the drawback of our this setup, right. So, one of the drawback is date time of mixing, and it will also not going to tell me, right, whether there is a formation of any intermediate state for such kind of experiment. Would not reveal any intermediate states in the reaction, right. So, what is the solution, right? Solution is, let us say if I have solution is single molecule level spectroscopy, single molecular fluorescence. Consider this situation that you have SF sitting over here and somehow you are just monitoring this SF, right. So, EQ will come and interact and will go, right. So, now if I plot, so this is my single molecule, right, you are monitoring single molecule fluorescence in this case. So, in this case if you just sit and look at this SF molecule as a function of time, what you are going to see, right. SF, this F is present, but it is attached to S. So, let me define this intensity as is fluorescent, but weak, weak fluorescence, and this F is strong fluorescence when it is free from S. Right. So, in this case what you are going to see is that there is some fluorescence intensity, right. So, the fluorescence intensity is like this, let us say, but when this EQ, sorry, I should write this weak fluorescence not here but here, but when it is this form obviously the Q is nearby, that is So, that means very weak fluorescence. So, this one is very weak fluorescence, this one. Okay. So, the fluorescence intensity of SF you are looking here, right, is like this, but when this EQ binds to SF, the fluorescence intensity will decrease. So, you will going to see a decrease in the fluorescence intensity, and that fluorescence intensity in the low fluorescence intensity region will stay for some time, and then when the reaction will takes place, when the reaction will finish, right, then there will be a formation of S and F, the free F. So, the free F fluorescence intensity will be there if you are still looking this F, right. If this F will go away, then obviously we will not be able to see, but consider that you are still looking this thing, then the fluorescence intensity will increase like this. The fluorescence intensity will increase, right. That means I have both my SF and EQ in the solution. I am just only looking at the SF. All of them are there. So, if SF is alone, right, then I see a moderately fluorescence intensity. When EQ come and interacted with SF, then fluorescence will decrease, and that reaction will take its own time, and then when the reaction is over, it is forming S plus F, and the fluorescence intensity again will increase. So, if I do this thing several times, then I will get a clear idea about what is the rate of this enzymatic reaction. Here the plus point is that there is no dead time of mixing, right, because all the substances are present in the solution in beforehand. Only what you are doing, you are monitoring the SF, right, EQ is already present. So, unlike this, right, if let us say the reaction will takes place in 1 second and your dead time, you are mixing very slowly, like it took 10 seconds, then by the time you mix, shake, reaction is over, right, you will not be able to see such kind of rise. But in this case, you will be able to see that such kind of reaction, because all the molecules are present, reaction mixture. Another important information what we are going to see is that whether there is a formation of any intermediate state. Let us say the fluorescence intensity of this reaction is not like what I have shown in this green, but it is like this one, and then decreased, and then is like this, and then it increased and remain like this, and then again increased and it become like this. So, clearly I can tell that here is my SF, here is my S plus F, that is for sure. In between that SF must have interacted with EQ, that is why fluorescence intensity is less, and in this intermediate one the structure must be SF, little bit of different type of interaction with EQ. That means, you will be able to see this intermediate state very easily if you monitor such kind of single molecular level fluorescence. Okay, let me finish here and we will continue our discussion in the next lecture. Thank you very much.